Hi and welcome again to my Physics Online video lecture supplement series. Today's video I'm going to be looking at fluid dynamics, and this is actually the second part of the fluid dynamics lecture in which I'm going to be looking at viscosity and turbulence, and I'm going to be looking at those both together and in turn. So as I noted in the first lecture part, there are two basic types of flow that fluid will undergo. The first one, which was the main focus of the last lecture and will in fact be looked at a little more in depth in this lecture, is laminar flow, which is basically smooth flowing between different layers in the fluid with no mixing from one layer to the next. The other type is turbulent flow, and that's going to be looked at a little bit later on in this lecture. And that is basically flow in which there's some swirling. You could say there's an angular momentum component to the fluids, and the result is that different layers maybe mix a little bit more. And so we're going to look at both of these types of flow throughout the lecture. And then the other thing that we're interested here, besides laminar versus turbulent flow, is what's called viscosity. And viscosity you could think of as a measure of the friction between different layers within a fluid. And so viscosity itself tends to be measured under the condition when we have laminar flow, although it ultimately can help cause turbulence. And the other thing about viscosity is, and if you've been watching these lectures and paying attention in my class on campus, you maybe already know this. Viscosity helps to cause the drag force that's called the Stokes drag for a fluid. You'll recall that the Stokes drag has a term in it that is a measure of the viscosity of the fluid. So the first thing to look at here is what happens when we have laminar flow and what happens when we have turbulent flow, and what are the different layers of a fluid doing. And one way of looking at how different layers behave is to look at what's called the streamlines in the fluid. And what a streamline is it is a representation of the local velocity of a volume of the fluid. So right here we have a diagram that shows a fluid that's flowing. There's several layers within the fluid. Each layer maybe has a slightly different local flow rate, has a different volume flow rate, has a different speed for any given particle within the fluid. And you'll notice that basically as you move towards the surface in this case, the fluid gets to be flowing a little bit faster and faster and faster until you get to the surface where it's at the fastest. And so there are different layers within the fluid. Each layer can be approximated as being the fluid which is moving at this particular velocity. And you see that all the velocities are more or less parallel to each other. There can be a little bit of non-parallel flow. For example, right here, these are still reasonably laminar. This right here is still reasonably laminar. But when we get into turbulent flow, there starts to be this little bit of mixing going on, where one layer's velocity will pick up an angular momentum component that forces it into the other layer, and vice versa. So these little whirls are basically turbulence. And so what has happened here is that we've gone from these smooth, sort of segregated streamlines into this mixing stream in which all the streamlines are basically broken. So we don't have a continuous streamline from here all to here. Instead we get to maybe here, and then it starts to break up and swirl, and then maybe some streamlines get reestablished. So what is viscosity? What it is it is a sort of measure of the frictional force between successive layers within a fluid. And these layers, of course, then have to be moving with respect to each other. If there's no motion, then you have a sort of static friction, and that's the end of it. But viscosity is more interested usually in kinetic friction or kinetic drag. And what it is caused by is the cohesive forces within liquids, or if you have a gas, then it's caused by the collision between molecules in the gas. And we can quantify it, meaning we can put a number to it using the parameter eta, which is called the coefficient of viscosity. And sometimes people just call eta the viscosity. It is in fact a measurement of the viscosity. And we'll look at how we can measure that in a moment. It's worth noting that the SI unit for the coefficient of viscosity is Pascal seconds or Newton seconds per meter squared. It's also worth noting that this quantitative parameter for the viscosity is proportional to just how viscous the fluid is. That may seem tautological, but there it is. Basically, the larger that this coefficient is, the more viscous the fluid is, and therefore the more friction there is between successive layers in the fluid. Similarly, the more drag force there will be on any object that is trying to pass through the fluid. So how do we measure the viscosity? The answer is that what we do is we place a fluid between a pair of plates. So there's a moving plate and there's a stationary plate. And then we pull the moving plate so that it moves at some constant velocity along the top layer of the fluid. And we measure what force we have to pull with in order to get the plate to move at this constant velocity along the fluid. And so it turns out that this force depends on several factors. One is the area of the plate which is in contact with the fluid. One is the distance between the two plates, so how thick is the fluid. And then one is just how fast are we actually pulling this plate at. And then last but not least, you knew that this one had to go in there somewhere because it's what we're trying to measure. The viscosity is also a factor. And so the force itself is equal to the viscosity, or coefficient of viscosity, times the area times the speed divided by the length. And so we solve this equation for the coefficient of viscosity, and we get force times length divided by speed times area. So let's go ahead and work a couple of examples for this. And one way that we can work these examples is we're going to need to use, at least to answer this first one, a table of values for the actual fluid viscosity. And so that table actually is on the next slide. So let's go ahead and answer this first question first. So we're trying to figure out how much force is required to drag a plate given the plate's cross-sectional area, given the speed that we're dragging it at, and given that we're dragging it through water with a known depth. And so what we have to do is open up a table of values and try and find out what the viscosity of water is at 20 degrees C. So it turns out that this slide, the next slide in my lecture notes, has a table of different viscosity values for a variety of fluids, including both gases and liquids. And here we see water on the slide, and water has a value at 20 degrees C of 1.002. And we look up at the units and we see that that is actually millipascal.seconds. So if we want to put this in Pascal seconds, in other words, if we want to get our force to come out in newtons, then we're going to have to put this in Pascal seconds by basically multiplying this by 10 to the minus 3 to convert from millipascal to Pascal. So basically we can write down that we have eta equals 1.002 times 10 to the minus 3 Pascal seconds. And we saw that the force is given by the this coefficient of viscosity times the area times the speed that we're dragging with divided by the depth of the water. So looking at these terms, this one right here is 12.5 centimeters squared, but but we got to convert that into meters squared, and so we do that by dividing by 100 twice. So that's going to give us 1.25 times 10 to the minus 3 square meters. This one right here, this is our length. Also, we will want to have in meters, so 0.0875 meters. So we have basically 1.002 times 10 to the minus 3 Pascal seconds times 1.25 times 10 to the minus 3 meters squared times 1.25 meters per second divided by 8.75 times 10 to the minus 2 meters. So if you do all of that, what you'll end up getting is that you'll find that the force is approximately 1.789, so maybe 1.79 if we keep 3 significant figures, times 10 to the minus 5 newtons. So that's how much force we would need to pull on this plate in order to keep dragging it at 1.25 meters per second. And the follow-up question is, what happens or what changes if we drag this through olive oil at the same speed, temperature, and depth? So if you look up in that same table the viscosity for olive oil, so for water it was 1.002 times 10 to the minus 3. For olive oil it ends up being 138 times 10 to the minus 3 Pascal seconds. So if this is the force needed to drag through water, then to get the force needed to go through oil, we can basically repeat the whole process but substituting this number for this number, because that's the only thing that has changed. And what we end up with is about 2.46 times 10 to the minus 3 newtons. So that is how much force we need to drag under all the same conditions this plate through olive oil instead. So now that we've looked a little bit at how to calculate viscosity, let's look at what it actually does to a fluid. And one way of looking at what viscosity does to a fluid is to consider the flow of a viscous fluid through a tube. So this is actually quite an interesting topic, especially for those of you who are more biomedical students that are taking physics as part of your biomedical program. And the reason why this is interesting is because whenever you study stuff like the flow of blood through an artery or a vein or what have you, through any kind of blood vessel, you are in fact looking at a viscous fluid in a tube. And in fact, that actually is what motivated the original studies of this. The original studies of this that we know of were by the French scientist J.L. Pouseuille. And he was actually interested in exactly the question of what happens while blood is flowing through veins and arteries. And what happens is that if you have a non-viscous fluid, then if it's a smooth-sided tube, then basically you'll have every layer having about the same velocity through the tube. But when you add viscosity in, that means that there's drag both between different layers within the fluid and also between the outermost layer and the wall of the tube. And so what tends to happen is that the outermost layer of the fluid flows more slowly than the innermost layer. And so basically the speed increases as you go in and then starts decreasing as you go out because, again, the walls of the tube are stationary. And what basically happens is that you have to have some amount of work to keep the fluid itself flowing. And the work itself, what gives us the work, is that there is a pressure difference between the ends of the tubes, and therefore there's a pressure difference throughout the fluid. So the pressure here is lower than it is here, in other words. With the laminar flow, what you end up having is something like Bernoulli's equation that we previously discussed, and no work done by friction term in that equation. But if you want to include a viscous fluid, then Bernoulli's equation has to be modified to also include work done within this fluid due to friction between successive layers. And so basically that is also what helps cause this difference in speeds and flow speeds for the outermost layer versus for the innermost layer. So let's look at Pousseille's equation, because basically what that does is it'll allow us to quantify exactly what happens to this fluid as it's flowing through a container. What we basically have is a volume flow rate Q. Remember that Q is how much volume of the fluid flows per unit time. So how many liters per second, or how many cubic meters per second. And it turns out that this volume flow rate through a tube is going to depend on a few different factors. One of them is called the pressure gradient. It's basically how much does the pressure drop over the tube divided by how long is the tube. In other words, it's the change in pressure per unit length. That's what's supplying, again, the work that's being done to this fluid as it flows through the tube. Another is, of course, the viscosity, because that's going to be the resistance to the flow. So this is helping drive the flow, this is resisting that flow. And then yet another thing that this depends upon is how big around the tube is. Again, recall that if you're trying to measure the viscosity, you can measure the force that it takes to drag an object across the surface of water if the bottom of the fluid, the water or whatever fluid you're using, is against a stationary plate. And that one of the terms in this was a length term that basically determines how high the plate that you're dragging is above the plate that's stationary. In other words, how deep is the fluid? Well, this radius of the tube term basically is the same effect. You could think of the innermost fluid as being the thing that's actually being pulled across the surface at the top, and you could think of the wall of the tube as being the stationary layer. So this radius term r is equivalent to the length term L that we previously used to mean the height or the depth of the fluid. Unfortunately, this means that we now have two capital L's in this lecture. One has meant the depth of the water in the measurement of the viscosity experiment. The other one now means length of the tube. So you'll have to keep those two things straight if you're just looking at the equations. In any case, there's the equation basically says that the flow rate is the pressure difference divided by what's called the resistance to flow, capital R. So this R is not the radius, it is in fact the resistance to flow. And that resistance to flow is given by 8 times the viscosity coefficient times the length of the tube divided by pi times the radius to the 4th power. Or in other words, if we substitute this equation in for capital R, the volume flow rate is pi times r to the 4th times the pressure drop divided by 8 times the viscosity times the length of the fluid, of the tube, that is. And we're assuming here that we have a liquid, in other words, a non-compressible fluid. So it's not a plasma, it's not a gas, those things are compressible. The most interesting thing, I think, in this equation to look at is that it depends on r to the 4th power. That's a very strong dependence on r. The result of that is that a very small change in the tube radius can lead to a very large change in the volume flow rate. So for example, if you have a tube size and you reduce it by only 10%, you'll actually reduce the flow rate by 35%. That's 3 times as much of a reduction in flow rate and then some, as you had a reduction in the actual tube radius. So here's an interesting application of all that for those of you who are, especially for biomedical people, but in general. What happens when plaque starts building up on the inside of a blood vessel? That starts to narrow the radius of the tube, the effective radius of the tube. So what's going to happen to the volume flow rate when plaque builds up? Incidentally, plaque can also introduce turbulence by, for example, building up not uniformly. So it gives a sort of sharp barrier, kind of like the rock shown on the first page of this notes. Or I guess this is actually technically the second page, or third if you count the title page. But I'm referring, of course, to this rock right here. Or this, if it's not a rock, then maybe it's like a mound of sand or whatever that's built up in the bed of the stream of water. It gives you a barrier, and what happens is that water collides with it, and that tends to cause turbulence. So one effect of plaque is that it can introduce some turbulence into the blood. The other effect, though, is that it narrows the blood vessel and therefore reduces the volume flow rate of the blood through the vessel quite drastically for even a small amount of plaque buildup. So let's look at a couple examples of actual volume flow rate and also resistance to flow for blood as it travels through an artery. And we'll start with this one, which gives us the question, what's the resistance to flow, that's capital R, for whole blood at 37 degrees C while traveling through a 25 centimeter long artery with a diameter 0.045 centimeter. So the resistance to flow is given by this equation. R is 8 times the coefficient of viscosity times the length term divided by pi times r to the fourth. So we need to get the viscosity at 37 degrees C, which is roughly what your internal body temperature is, for whole blood. And looking at the table here, we see that whole blood at 37 degrees C has a viscosity of 2.084 millipascal second. So basically what we have here is that R is 8 times 2.084 by 10 to the minus 3 Pascal seconds times the length, which was 0.25 meters. And then in the denominator we have pi times 4.5 by 10 to the minus 4 meters, and then that number is raised to the power of 4. So if we plug all those into our calculator, we get that the resistance to flow is approximately 3.235, so I guess 3.2 times 10 to the plus 10, and again the units for this are actually Newton times second divided by meters to the fifth power. So that may be kind of an odd unit. You could also formulate this as 3.2 times 10 to the 10 Pascal seconds per meter cubed. So either of those is a valid way of expressing these units. The second part of this question is, if the pressure drop across the above artery is by 24 millimeters of mercury, what is the volume flow rate of the blood? So recall that we can write the volume flow rate Q to be P1 minus P2 over R, or in other words, delta P over R. And so all we got to do is convert this right here into actual SI units. So one way of doing that is to remember that 760 millimeters of mercury is equal to 1 atmosphere, and that's also equal to about 101 kilopascals. So those are equivalent unit. So what this means is that this 24 millimeters of mercury is actually more like 3,200 pascals. And so divide that by the resistance that we just found, which was 3.2 times 10 to the 10, and that was in Pascal seconds per cubic meter. And what we end up getting here, noting that this is the same as 3.2 times 10 to the 3, is that our volume flow rate is about 1 times 10 to the minus 7. You see that the pascals cancel, and we're left with a seconds over meter cubed in the denominator, which is the same as meters cubed per second. So we have actually a nice round volume flow rate. So the circulatory system as a whole basically can be modeled by using Pousseille's equation. And again, that's actually what helped motivate Pousseille to conduct all these experiments and eventually formulate this equation. And basically how this works is you start off with the heart. You've got a very large artery, maybe the aorta, and also a very large initial pressure, and then the pressure drops as the volume flows through the system, and moreover the arteries basically split into smaller arteries, and then into arterioles, and then into capillaries, and eventually into venules and veins. And then by the time we return back to the heart again, it's actually blood at very low pressure. So then the heart pumps the blood through the lungs, so it's relatively high pressure, goes through the lungs, gets oxygenated, then goes back to the heart to get pumped back out into the rest of the body. And among other things, what we find is that as the arteries split into many smaller arteries, you may have that these smaller arteries have the same total cross-sectional area, and it may be even that if you were to add up the radii of each individual small artery or arteriole, that it's about equal to the main area and basically radius of the primary artery. You'll find that the volume flow rate actually ends up dropping. And the reason why that is, one, is because the pressure is lower, but also two, the R to the fourth term becomes much smaller for any given small artery. And so the result is that Q drops, and that also means that V must decrease. So the speed at which the blood is flowing decreases as we go into these very small capillaries. And what that does is that it basically allows the blood to actually interact with whatever part of the body the blood happens to be supplying oxygen and nutrients and what have you to. So that's basically how the circulatory system works. And then as these capillaries rejoin with the main vein, then all this blood ends up returning to the heart, and the process basically starts over again. So now that we've looked a bit at viscosity and what viscosity does in laminar flow and so on, we can move on to the other interesting topic, which is turbulence. And there's actually two things that can cause turbulence, and I've basically hinted at both of them or stated one of them outright so far in this lecture. The first is actual obstructions, which again I stated that outright by going back to that pile of sand or rock or whatever it is in the fluid stream. This is basically an obstruction, and what happens is when the fluid hits an obstruction, the obstruction imparts some acceleration to the fluid that has a perpendicular component to the initial velocity of the fluid. And so what that basically means is that there's going to be some perpendicular velocity components imparted to this fluid. So whereas it may initially have been like this, flowing as a nice laminar flow, when it hits this obstruction, these top layers end up kind of turning down into the middle layers and you start getting mixing. The second thing that can cause turbulence is that when fluids start moving at high enough speeds, the drag forces between layers becomes very large. And in particular, the drag force between the outermost layer and the wall becomes very large. And how large it is going to depend upon how fast the fluid is moving. Remember Stokes law drag, the force goes like velocity to the first power, but it also depends upon the viscosity of the fluid. Again, Stokes law drag goes like viscosity to the first power. And so what happens is that these very high drag forces end up essentially causing some fluid mixing, especially if the walls of the fluid have any amount of turning, no matter how gradual. So one way of measuring the onset of turbulence, or of determining when turbulence is going to happen due to high speed of fluid flow, is to use what's called the Reynolds number. And Reynolds number basically is a number that you calculate. It can have any value that is positive. What we find is that usually if Reynolds number is less than 2000, you're going to have a laminar flow, provided of course that there's no obstructions. If Reynolds number is greater than about 3000, then the flow is going to be turbulent for the most part. And somewhere between 2000 and 3000, the flow starts to become unstable. It means it starts transitioning from laminar to turbulent flow. And so this right here is where we see some transitioning from laminar to turbulent flow, this region with V2. The region with V1, Reynolds number must be less than 2000. It's pretty laminar. And over here at V3, there's a lot of turbulence, and so Reynolds number must be larger than 3000. So you can calculate Reynolds number based on the density of the fluid, based on the speed of the fluid, based on the radius of the tube that the fluid's flowing through, and based on the viscosity. It's given basically by this equation. There's an alternative thing that's useful, which is what happens if there's an obstruction. And one way of looking at that is the motion of an object through a fluid is not very easily distinguishable. In fact, in many cases we would say is indistinguishable from the motion of a fluid around a stationary object. So what happens is that the relative velocity between the fluid and the object becomes the only thing that really matters. And you can have either laminar flow around the object or turbulent flow around the object or some combination thereof. And what we use is a modified version of Reynolds number, sometimes denoted N prime. And how it is determined is that it is rho, the density of the fluid, times V, the speed, the relative speed between fluid and object, times L divided by eta. So eta is the viscosity. L is a characteristic length of the object. So for example, if this is a spherical ball, then L would represent the diameter of the ball. So that's your characteristic length. If it was a cube block, then maybe it would be the length of each side of the face, or the length of the diagonal maybe could be used. And it turns out that there's actually 4 regimes of interest in the case of fluid moving around an object. So if this modified Reynolds number is less than 1, then you have laminar flow. If it is greater than 1 million, then you have entirely turbulent flow around it. Now, the 2 in-between regions are from 1 to 10, in which case usually you have turbulence in the wake of the flow. So this fluid is basically flowing around this object, and behind the object there is some turbulence. In front of the object, not so much. And somewhere between 10 and a million, you get what's called transitioning from turbulence, from laminar to turbulence. So that means that instead of just having turbulence here behind the object, you start getting turbulence all around the object. So this one right here is probably close to 10 to the 6th for a modified Reynolds number. This one maybe is closer to about 9 or 10 as a Reynolds number. Somewhere in there you'll start getting turbulence, say, here. Somewhere else you'll get turbulence onsetting here. Somewhere else you'll get turbulence onsetting here, and so on. The separation points are the points on the object at which the laminar flow lines basically separate out and hit turbulence, basically. So laminar flow, the lines would basically go kind of around the object like this. Here you see that they start going around the object and they leave from the object, and at that point they start becoming turbulent. So that's what the relevance of these separation points is. And since we've been talking about it throughout this lecture, I thought it'd be nice to bring back up there's a Stokes law drag force. And we've talked about it before, but as a reminder, the equation for Stokes law drag is that the drag force, or the Stokes force, is 6 times pi times the radius of your object times the viscosity of the fluid times the speed of the fluid with respect to the fluid. So this v is your relative speed term. And so this right here applies specifically to the case of a small sphere moving in a viscous fluid. If you have a non-spherical object, then you end up with a similar appearing force. It's still probably linear with the speed. It's still linear with the viscosity. And it's just this geometric term 6 pi r that gets modified. So there's one other topic of interest that I suppose is best discussed again here, which is I think that I previously discussed lift in discussing fluid flow. How does an airplane fly, basically? There's a second term which is important, which is the drag term. So what the lift comes from is that it's the difference in air pressure above the wing versus the pressure below the wing. So here is sort of like a side view of an airplane wing. The wing is shaped and angled in such a way that the air flowing above it will flow very rapidly above it and very slowly below it. And as you know from Bernoulli's principle, as you increase the speed of a fluid, you decrease the pressure. So if you have very high speed above the wing, then you're going to tend to have very low pressure. And so there's a net difference in pressure here and here, and that also means that there's a net force upwards on the wing. And so that's how an airplane gets lifted. However, there's also drag. And drag causes the plane to slow down, which also, by the way, causes the relative speeds above and below to slow down, thereby decreasing the lift. And so the drag actually has to be overcome by the airplane's engines. And what all of this actually does is it imposes a maximum speed for the plane given the plane's wing size. Basically, the larger that are the wings, the less that you will have pressure difference in order to get the same force per unit area. And so then maybe you also have to factor in that the larger wings also add mass and so on. On the other hand, larger wings mean a larger surface area over which there can be drag, and therefore greater drag, and therefore lesser speed, and therefore also lesser pressure. What all of this does is it imposes actually an optimum wing size for an airplane, because the bigger the wing, the more lift you get, but also the more drag. And the more drag, the slower you go, and therefore you start losing lift. So that's all that I wanted to talk about in today's video lecture. So this has been a lecture predominantly about viscosity and the difference between laminar and turbulent flow and how viscosity affects the turbulence of a flow. Hopefully you have enjoyed this lecture. I hope that it's helpful to you in your studies, and thanks for watching.